We are very fortunate to have Dr. Ed Ting with us from Avure Technologies Incorporation. Ed is the Vice President of Research and Development with Avure, and he's located in Kent, Washington. He started high-pressure work in 1993 at Avure. He's currently working on shelf-stable, low-acid foods and other advanced high-pressure applications. He graduated from MIT, Massachusetts Institute of Technology, in materials science with his master's, and Northeastern University in mechanical engineering with his bachelor's. And Ed is going to be talking to us this morning about commercialization of high-pressure processing. Ed.
Okay, can you hear me? Am I on? All right. Okay, it's a great pleasure to be here. What I want to try to accomplish in the next hour or so is to give you a very broad overview of the history of high pressure, kind of its current status, hopefully answer many of your common questions that you have. I'm not going to go into a lot of depth. There is a tremendous amount of literature already out there, unlike when it started around the early 90s. So, and if there is time at the end, I would like to show you a promotional video made by the Hormel Foods Corporation in their marketing campaign to sell their high-pressure process product. So let's talk about the commercialization of high-pressure processing. At the end of this presentation, I'm going to make some comments about what is necessary to take a technology into the real world. And these comments are, of course, from my experience in high pressure, but really they would apply to any new technology, whether it's, RF, PEF, or any of these technologies that we've been hearing about. High pressure is, in some sense, not new. It's been scientifically reported since the 1890s. So it's taken it over 100 years to become commercial. A lot of renewed science took place in the 80s, focused directly on food products. And previous to that, in the 40s and 50s and 60s, a lot happened in the engineering world that allowed the engineers to build commercial systems. Commercial systems being big systems that would run around the clock to make commercial products. In the 1890s, the first researchers were using cast iron pressure vessels. I mean, they did not even understand the makings of modern steel or stainless steel. So it's quite a statement, for these people in the early 1890s to have pursued high pressure research. High pressure research took big steps in the 1940s. Percy Bridgman won a Nobel Prize for his work with high pressure. He did a lot of work to characterize the effect of pressure on all sorts of things, from polymers to foods to proteins, and that kind of set the stage for the commercialization of this technology, which first took place in the 1990s out of Japan. And in 2004, we estimated that the commercial products being produced was already over $500 million. And probably this year, it will be, in 2006, it'll probably go over $1 billion worth of product. That's high-pressure process. Quick comment about Avure. What is Avure? Is this a French company? No, it's a made-up name. Some marketing genius wanted to coin a unique term. But the history of our company goes back many years. It goes back to ASEA, which is a Scandinavian-Swedish company in the 1950s. They were out to be the first to make synthetic diamond, or rather man-made high-pressure diamond, and they developed a lot of the preliminary high-pressure technology. They became ABB Pressure Systems, and in the United States, a company called Flow Industries grew in the 1970s out of SBIR type of initial funding into Flow International. And Flow International acquired the Swedish ABB Pressure Systems Group in 1999. And the sum of the parts became Fresher Under Pressure, and now it is Avure Technologies. So we heard about what consumers want. I'm going to talk about what you want. Industry. Industry wants what? Wants profit. This is not a charitable organization. Industry is out to make profit, and you do that by having more sale and better products. And high pressure is one approach to getting there. It's certainly not the only approach, and high pressure fits kind of a certain set of the technology. High pressure, what can high pressure offer? Definitely it has antimicrobial effects, which is great for food safety, which I would consider part of quality. I wouldn't call a product good quality unless it was safe. But also in terms of higher sensory quality, longer shelf life. High pressure delivers great consumer acceptance. Like it or not, whether it is a proper perception or not. I mean, consumers don't understand how high pressure kills, but nevertheless, they feel they do. They have high pressure in their automobile tire. They pump it into the bicycle. They put it into the basketball. It is not an intimidating thing. So, rightly or wrongly, consumers accept it. This is a gift, and deal with it, I guess, is the answer. As a result of the quality you can get and the consumer acceptance you can get, there are many new business opportunities that can come out of this. So this presentation is going to cover these aspects: the process overview, the benefits, some aspects of microbiology, some aspects of the regulatory issues, a look at what it costs. This is always a big question. The big questions is how does it work and what does it cost? Those are the two big questions that you always get asked with any new technology. And then some closing comments on what are the keys to commercializing a technology. So, what is this? And what does this have in common with this? Well, the answer is that they're both high pressure treated. The first one was a hip implant made out of powdered metals. It's high pressure treated to densify it from powder into a solid piece that a surgeon can put into your hip. The second photograph was with lobster meat that's been separated from the shell, still in the raw state. Now, if any of you are familiar with the seafood business, that product was never ever available before. There was no way of taking raw meat out of a lobster, period. The only way that people could do it in the past was to cook the lobster and then the meat falls out. But by doing that, you lose a lot of moisture, you lose weight, your yield is poor, you don't get all of the meat out. With high pressure, I'll show you a little video later, you can get every bit of it out. So productivity gain, yield gain is a great justification. And that application has nothing to do with microbiology. It's purely a functional benefit of high pressure. So, going back to the origin, this is a photograph of one of the earliest presses used to make diamond. You all know that diamond is nothing but carbon, and at high enough pressures and temperature, you can convert graphite into diamond. And through that race, our predecessors at Avir developed the pressure vessel technology. That's a laser, right? You can see this familiar shape is going to show itself in many future photographs. That represents a wire-wound yoke or frame. This is what holds the cork in the pressure bottle, basically. And this technology was developed in the 50s and has matured ever since into the commercial systems of today. The commercial industrial processing is still a big business. In fact, this is the bigger business for Avir. We build these presses for consolidating everything from ceramic to metal, you name it. A lot of these applications are dealing with densifying particulate materials, whether it's silicon carbide, alumina, powder metal, aluminum, whatever. Every jet airplane you fly in has turbine blades that have run through a hot isostatic press to basically heal the casting defects that exist in those blades so that you can get very good reliability out of them. Oops. The other side of the family tree comes out of Flow International that was developed in the 70s with water jet technology. We develop high-pressure pumps that are used to do all sorts of industrial cutting and cleaning applications. This photograph shows a fish portioning system. In fact, these are all commercial systems. We sell our nozzles, or at least I should say we, Flow International. We're no longer part of Flow International because we were sold recently. But Flow International builds high-pressure pumps and nozzles that are sold to system integrators. For example, FMC, they incorporate them into robotic cutting systems for fish portioning. And this is what a system would look like. Through the course of water jet development, a lot of material science, mechanical engineering technology was perfected. This is a photograph of a diesel engine powered high pressure pump. That's 150 horsepower. What is unique about this pump is that the cylinders on this pump are alternating between zero pressure and 40,000 psi pressure 2,000 times a minute. And if you're a mechanical engineer, you could appreciate the fatigue that takes place out of structures like that. You all remember not recently, but I saw on TV just the other night, they had a news story about the Aloha airplane that became a convertible mid-flight because of metal fatigue. Well, that is the same phenomenon that would destroy pressure vessels. And to have this kind of mechanical performance is really a great step forward in the metallurgy and engineering. So the high pressure water that's generated out of these pumps is used for all sorts of things, from removing paint to destroying concrete. So for Flow, the question was asked in the 1990s, we use high pressure water to destroy concrete, cut baby diapers, cut fish, cut steel, cut aluminum. Why can't we use it to squirt juice? So that was kind of the inspiration, and the rest is kind of history. So what sort of pressures are we dealing with? Typically, the pressure that goes into this pressure vessel is on the magnitude of about 80,000 psi for many applications. Some applications, especially the non-microbiological ones, are at probably half of that pressure, so quite a bit lower. In comparison, the pressure at the deepest part of the ocean, if you go out to the Marianas Trench, deepest part you can get to is about 16,000 psi. So that gives you a relative comparison. So we are at pressures that no living organisms has ever experienced. And there is a lot of science here. I think what Pat Dunn said is very true. There's some very fundamental science to be done with understanding how high pressure inactivates microorganisms, which is probably related to how proteins denature, which is probably related to Gibbs free energy terms of entropy effects. So we're not going to look at that today. What is a high pressure system? Basically, it consists of a tank, a cylinder, into which you put water, and then you close up the cylinder, and then you pump more water into the cylinder. Because at these pressures, water is compressible. As Paula said, typically 15% and higher, depending on temperature primarily. So you use a physical displacement pump. You use something like a piston pump that physically crams in 15% more water. So if I had a 100-liter vessel, I would have to physically force in there 15 extra liters to get it up to 80-some thousand psi. At the end of the process, you open a decompression valve. That extra water is vented out, is jetted out, and then the system opens up and your product comes out. It's a very simple process in concept. How do we make that pressure? The pressure is made with a positive displacement pump. It's an intensifier pump. Basically, you have a small piston, as represented by these two cylinders, fixed to a larger diameter piston, and this surface area ratio difference is what sets the amplification ratio. So if there is 10 square inches here and 2 square inches here, That's a factor of 5. Every 1 psi here becomes 5 psi there. So it's a very simple mechanical concept. The trick is to make these components last, to make the cylinders last, make the valves last, make the seals last. So this is a typical vertical system that we manufacture. You can see here's the bore. The product is typically put in here, and here's the closure mechanism. And you can't quite see it, but here is that elliptical frame that was shown on the black and white photograph. This person is actually standing on the platform. This is only about the top third of the system. The rest of it is underneath the work area. Underneath this person's will be the pump, the water holding tanks, and all of those other equipment. This is one of the high pressure pumps. In food processing, throughput is essential. You cannot afford to take 20 minutes to get to pressure. So as Paula said, high pressure come up is purely an issue of economics, and most frequently it is a no-brainer to add more horsepower to the pumping system so you can come up faster, because time is money. So this system shows 4 intensifiers, and these are all hooked up in parallel. So they're not sequential, they're in parallel purely for more output. And in reality, the current systems that we're installing actually has 2 pumps and a total of 8 intensifiers. And that allows you to get up to pressure in 2 minutes or so for a large system. This is a plant showing there's 2 machines, one right behind the other. This plant is located in Mexico, and because of the labor there is relatively cheap, the product handling is done just with overhead crane and human operators. Depending on companies' requirements, it could be fully automated, or it could be as simple as this approach. You can again see the unique characteristic, the shape of the wire-wound pressure vessel. I should say a word about that. The reason we use wire winding, this vessel is basically wound with miles of high tensile strength wire. The reason is, just like for food processing, the rate at which you can pull heat out of the can depends on the size of the can. If you're building large metal structures like this, you cannot cool them fast enough to heat treat them to the right strength levels. So we use wire. Wires is independent of the size that it is wound to. So whether we wind a small cylinder or wind a big cylinder, its mechanical properties are the same. So this is the key difference between wire winding technology and monolithic technology. If you cut this frame out of solid metal, you'll have a very hard time to quench it at the right rate to get the strength properties that you want. This is one of our newer machines. This is a horizontal orientation machine. This machine is very unique. It's actually going to be put on board a ship. A number of these machines are actually going out into the middle of the North Atlantic to process surf clams. As they dredge up these clams, they're going to be put into this high-pressure vessel, and they're going to be shucked using high pressure, and the shells are going to be thrown back overboard, and the meat's going to go into the freezer. This way they don't have to take people out there, and they can harvest a lot more clams because they don't have to store the shell. It's a very unique system, but we have systems like this for other applications as well. Let me address one of the common questions in regards to equipment. A lot of people think of high pressure as, a big physical risk. High pressure, what if it explodes? I'm going to leave a crater in the middle of Davis, Well, the point with this equation shows you that because water is only slightly compressible, the amount of contained energy in a high-pressure water-filled volume is quite a bit less than if it was an air system. If I had 90,000 psi air, now that would be a very big amount of stored energy. But because this is water, and water is only barely compressible, the amount of energy here is relatively low. And if you run the calculation, you see that the total amount of stored energy at 90,000 psi in a 215 liter processing vessel is roughly 20 megajoule. And in comparison, this is of the magnitude, maybe even less of a standard retort that you would have. Even though a retort is only at 30-some psi, because a retort contains compressible steam, which contains a huge amount of energy, whereas compressed water is only relatively small energy. So the takeaway message here is while high pressure does contain energy and does demand respect from the point of maintenance, it doesn't expose the producer to a higher magnitude of risk than what they're already dealing with. If you have a compressed gas bottle in your plant, that's probably 5 or 6 megajoules of energy right there. So high pressure, while it is an area that is regulated from the point of view of pressure safety, it is not a risk level that's way beyond what people are already dealing with.
2 points or comments maybe you'd elaborate on. One is you just said pressure safety. You have the same boiler code standards, essentially, depending on the size of vessel, as the retort person unit?
All high-pressure equipment gets regulated by one code or another, depending on location. Let me elaborate on this a little bit. In the United States, predominantly, the ASME, or the American Society of Mechanical Engineers, they have a special set of codes that regulate ultra-high pressure vessels. This is a code that's a little bit different than the steam boiler codes. So this is for very high pressure vessels. And for all practical purposes, most of the states within this country follow ASME, but there are exceptions. For example, Texas does not have a pressure vessel code. It has a steam boiler code. So in the state of Texas, pressure vessels are unregulated. But because we can't develop pressure vessels just for one state, our equipment is all ASME code stamped to meet the Section 8 Division 3 codes for ultra-high pressure vessels. In Europe, the pressure vessels codes are driven by the PED, or the Pressure Equipment Directive out of Europe. So pressure vessel construction is fairly well regulated in most locations. So that this regulation aspect is kind of good and bad because it slows down innovation, but it also kind of mitigates some risks with fly-by-night outfits building pressure vessels for you. So is that what?
Yeah, on the other side, it relates one to Bala's question. There's a company called EPSI that isn't located in Wisconsin, but they're in Massachusetts.
Yeah, EPSI is a Belgian company. They have a U.S. branch in Andover.
They're Andover, Mass. Well, they once were in Haverhill. The reason they're not there now is they had the hot isostatic press, the gas compression, and one of them blew up and their building's gone. So yes. This is the same thing as your bottle rocket, which is your compressed gas cylinder. But it was a whole lot bigger. You take a compressed
gas cylinder and you have it at 1,200 degrees Celsius, and then you uncork it. That is a huge amount of energy.
They were tempering the engine blades for the jet engines for the aircraft factory, GE turbine factory up in Lynn, Mass.
And there is a big difference between a high-pressure system that involves water and one that involves gas. From the pressure vessel code point of view, there is no distinction. So the food industry kind of benefits from that extra bit of safety. Not only are food systems regulated to the same extent as those high-temperature gas systems, behind it all, the energy levels in the food systems is quite a bit less. All right, so let's talk food safety, extended shelf life, new product possibilities, physical effects, cost reduction, regulatory benefits. These are all real benefits in the food area. In order to take advantage of these benefits, first of all, your product has to be suitable. High pressure isn't for everything. Okay, it's not going to replace heat processing. It's not going to replace a lot of other things. It won't do air-containing products, for example. You cannot process bread. You cannot process marshmallows. Those are not suitable products. And maybe even more, realistic, you cannot process whole apples because the core is basically a void, and you would collapse that apple. And in fact, you cannot process sliced cantaloupe because in the cantaloupe is a lot of air pockets, and you would end up changing the texture quite significantly. But there are some other products that can be processed very well. High pressure also requires you to have some water content. So can you process dried products? No. It doesn't work well microbiologically from that point of view. Almonds. California had problems with almonds and salmonella. Can you process dry almonds? No. The answer is no. But if you had some water activity in the almond, for example, if you soaked it first, then you could gain some benefit microbiological effects. The typical characteristics for the high-pressure treated products are products that have high value, heat sensitivity, preservative sensitivity, shelf life or pathogen concerns, or some other positive physical effect like the shell separation. Comparing to other processing method, high pressure really stands out. It is not thermal, it is not a chemical base, it is not a radiation base, it's not it really fits into a unique niche. There is no disclosure requirement. Christine talked about this labeling issue. There is no labeling requirement for high pressure, so it's up to a company to label it or not label it. The consumer really doesn't need to know. I mean, the consumer doesn't know whether you're running it through a scraped surface heat exchanger, so what's the difference? Some people, and I think Avir belongs to that group, that we believe that consumers generally want to know, especially when new technology is introduced, and we are supporters of clearly identifying what technology is involved, even though legally there's no requirement. So right now, with the term pasteurization being broadened to include other technologies, it's our opinion that companies should say pasteurized by high pressure, rather than just say this is a pasteurized product. I think there is some room for abuse if you leave out that qualifier. That's a political issue. Here are some examples of products. These are smoothie products. And in the juice area, the quality benefits and nutritional benefits are very, very obvious. If you look at vitamin C retention as a function of pressure here for fresh orange juice, folic acid in orange juice, many of these important nutritional components are unaffected by high pressure. There is no change in the sugar content, no final effect on pH. The sensory qualities are extremely good. Oregon State University did a pretty thorough test using a pretty large panel on high-pressure treated apple and orange juice, and the bottom line is statistically you cannot tell the difference between a high-pressure treated juice and a fresh squeezed counterpart. The real issue for the juice market is, does it have enough value to use this technology? And we'll get to that a little bit later on. This is the effects of high pressure on sugar. You see, this is truly a very minimal processing technology. Other areas would be things like ready-to-eat meat. This is a very significant market for high pressure, and this market is driven now in some ways by the new Listeria directive that came out of USDA. The USDA has now established different risk categories for ready-to-eat processed meats. There's the alternative. I don't know if you guys or any of you are in the meat business, but there's the alternative 1, 2, and 3. Basically, alternative 3 is a plant that only uses GMP for food safety. And if you're alternative 3, the USDA is in your face taking samples every other day. If you're alternative 1, they leave you alone. Alternative 1 represents the lowest risk, where you can demonstrate that you have an active intervention process at work and where there is no growth of any listeria that's in your product. I'll talk about that a little bit later, a little bit more. This is the guacamole product that's now very famous. This product, whether it's made by Calavo or Avomax or any of the other companies now doing it, is basically available countrywide. You can go to your local Costco and probably buy it.
That's Trader Joe's.
This is Trader Joe's. In the food service area, there are different formats. This is just kind of bulk avocado. There's avocado halves. There's salsa. Cisco is a distributor of this product, and it's gotten very good reception. In the juice area, there's a number of products on the market internationally. One of the big areas for juice is kind of a marketing area where the FDA is involved, and that's with the descriptor fresh. Can this product be called fresh? I don't think there's going to be an answer anytime soon. I think maybe the answer is no as of now, but if there are no nutritional differences and sensory difference, what is the definition of fresh? Juice does not grow on the tree. You have to process it to get juice. And you got to squeeze that apple to get juice. So, we say we squeeze it a little bit more. So, what's the difference? It's not that big an issue anymore. It may be a big issue for some juice products where its value is still somewhat marginal, and if they can get that descriptor, it simplifies the communication process with consumers and therefore add more value and therefore make that venture commercially successful. So it's somewhat of an issue, but not that big an issue. Okay, so there's a category, what I would call ready-to-cook products, such as these shucked oysters. These would go into oyster stews and things like that for restaurants. In fact, these products are kind of borderline also ready to eat because a lot of casinos buy this kind of product for their buffets. They are served on a half shell. There's a band that holds it together. The casino cuts it. They don't need the skilled labor to shuck the oyster. They can just plop open the shell and put it onto the counter. Now, in the whole ready-to-cook area, it's like this lobster meat. It offers great creativity options for the restaurants. Now, in the ready-to-cook area, this is the next big area for high pressure. In marinated, ready-to-cook meats, not only can you get the better effects of marination, but you can get longer shelf life and higher yield out of the meat. So this is a sample of a product that's been high-pressure marinated, and the control has spoiled very quickly, whereas the other one hasn't. So another take-home message is, if you think about the functional benefits, don't always think about the very high pressures. This is a powder metallurgy processing plant that you're looking at. This is the product carrier. Okay? Think of how many pounds of food you can put into this thing. So if you're working at low pressure, and the economics are very different. If you thought the high pressure is very expensive, that might be the case if you're using 87,000 psi to kill listeria in ham. But if you're using 20,000 psi to marinate meat, to unfold the protein so you can bind water into it better, it's a whole different scenario. So just keep thinking that there are a lot of creative opportunities. From one point of view, you can look at the market out there like this. There's a food safety axis. Okay, so if you think the food safety world, there are certain products that have known food safety issues, like sliced meats. And then there's a value creation axis, and a lot of the markets that are being developed are kind of in this quadrant. You have ready-to-eat meats, you have organic products. High pressure certainly fits organic. You have shellfish. Some other products don't work. Can you use it to treat water? Yes, but what for? There's nothing there to preserve. So thinking about the market opportunities it's a very important thing for food producers and entrepreneurs and companies. Okay, let's quickly talk about microbiology. You've seen many of this before. These are inoculated studies of listeria in ham, turkey, and roast beef. So these are, I did not label it here, but this is an 87,000 PSI application. The listeria is destroyed. In the control sample, listeria is very happy, even up to 60 days under refrigeration. There is no loss. An example of product that's high pressure treated and not high pressure treated. Now, one very good question that we dealt with early on with the USDA was, what about sublethally injured cells? If you run a process and you don't kill everything, what happens to those injured cells? Do they come back and get you? So what we did was we did this series of experiments where we looked at sliced turkey with low levels of antimicrobials. These are the lactates and things that are already used in products for flavoring agents. So even at those very low levels, we deliberately processed the sample so that there were survivors. And what you see is that the survivors die off over time. They do not grow out and get you later on. So this was one of the issues that we had to demonstrate, and that was done. In the oyster area, seafood area, as Bala said, Vibrio bacteria is another gift. For whatever reason, it is very sensitive to high pressure, and that's great for the people that like raw shellfish. So this work was done, in fact, by a number of researchers, including David Cook at the FDA, and they have published on all of it. The FSIS people have a new technology acceptance protocol, and basically what they wanted us to demonstrate was that our technology doesn't do these three things. It does not adversely affect the safety of the product, it does not jeopardize the safety of their inspection personnel, and it does not interfere with the inspection process. And we laid out all the documentation, all the information for them. It certainly does not do this. It is an anti-listeria step. It's actually a food safety benefit. It does not jeopardize the safety of the personnel because high-pressure equipment is highly regulated by state codes and by ASME. And it doesn't interfere with the inspection procedure because it is done in the package. So we were one of the very first companies to receive this USDA letter of no objection for high-pressure processing. I'll skip that. High pressure also allowed some companies to access markets that they couldn't otherwise. Abraham is a German company. They actually bought one of our competitors' machine in Germany, and now they're importing this product or these kinds of products into the U.S. They had a listeria problem, and what I'm told was that the USDA actually told them, why don't you use high pressure? And they did, and now I could buy this at my Fred Meyer, and this is an example of how high pressure opens a trade door that otherwise would be closed. Translate what? This? I don't know. Who can translate it?
Jenkins,
Okay. Excuse me?
I
don't know what that says. Can anybody read that? Excuse me? Okay, let's talk about cost a little bit. Okay, what determines equipment cost? Cycle time. There are some equipment utilization issues. Cycle time, your operational hours per year for your plant, and your product loading efficiency are two of the top issues. Cycle times means how long you keep the product in the machine. Okay, you got to be like Southwest Airlines. As soon as the plane unloads, you fill it up again, get it up in the air. And a minute sitting at the gate is a minute not making money. Same with a high pressure vessel. If it sits there, it's not making money. You got to get it around the clock. So most of the real serious operations are 20 hours a day, at least 7 days a week kind of operations. It is high capital equipment, as I will show, but if you use it wisely, it does pay itself off. And product loading efficiency is a concern. The other considerations are your depreciation rate. Are you going to treat this capital acquisition, with a 5-year depreciation, 7-year depreciation, or 10-year depreciation? Because all of this is going to impact your justification for technology. And then there's the factory cost for equipment other than high pressure. For example, automation. If you are in the U.S. where labor is expensive, you probably would want to have some form of automation, and the degree that you invest in it will be the amount of money that you can save later on. Then there are other cost issues like maintenance, labor, and energy. I'll elaborate a little bit on these. So here's an example of packing efficiency, how this impacts costs. If I have a circular pressure vessel, if I loaded it with cylindrical product, this is not a very high efficiency. All of this in-between space is wasted. This is real estate you've paid for, but you're not using. So this is not necessarily good. Now, you can optimize your package shape so that you occupy more of that volume. And obviously, the best efficiency is with a very large container the size of your pressure vessel. So we have worked with Scholey here to develop kind of a very large bulk transfer bag for processing primary ingredients, where that is processed and then you have an aseptic transfer that hooks it up later on to be dispensed into your final product. Product shape is important. So if you have semi-rigid bottles like PET bottles, you do have some stacking issues that you have to be conscious of. How you actually do this, it's an issue. How do you get people to individually place bottles in so that they nest so well? Well, this is not a realistic scenario. More realistically, you would have some sort of a highly flexible pouch, such as the guacamole pouch. That stuff you can just pour into the container, and it nests extremely well, and you can get a very high loading efficiency. If you have shaped products like ready-to-eat meat, that you can't do it that way. That there is some format that you have to do. You have to orient them in. The size of your processing vessel is important. So you have a small vessel, you're just not going to get the same efficiency. So you cannot make the argument that, well, rather than a single 215-liter vessel, I'm going to buy two 100-liter vessels. You're not going to get the same results. This is a very in-depth cost analysis, and you obviously cannot read this, so I extracted the factors onto these next two slides. So the things we're looking at in that spreadsheet would be things like, what is the cost per system, the number of systems you have, the number of weeks per year you operate, the number of days per week in operation, hours per day in operation, the number of employees that you have per shift, what you pay those employees, the cycles per hour per vessel, your electric power cost per kilowatt hour. All of these things are typically considered in projecting cost. And the bottom line of all of that is you come up with a total pounds total cost per pound. And I just have two columns here, one representing a 2-minute hold time and one representing a 3-minute hold time. So projecting a 2-minute hold time, it costs you about 3.8 cents a pound, using the assumptions that I have used. And if you ran it to 3-minute hold time, it costs you 4.7 cents a pound. This does not include the building cost, but this does include some depreciation cost of the equipment, but not of the building. So the lesson here is high pressure processing is sensitive to how long you treat the product for. So here's a word of advice to the academic people. Don't go studying processing times of 20 minutes and 30 minutes. Okay, nobody is going to use that data. It's just never going to fly at those kinds of processing times. But if you're looking at 30 seconds, 2 minutes, 3 minutes, these are within commercial possibilities. You can see here that about half of the cost of owning the equipment is the depreciation for the capital. Okay, so this is something that this technology has to deal with. Okay, some last comments on what it takes to succeed in the commercial market. You have a new technology, so what do you got to do? Well, you got to pass the regulators. You got to show that it's safe. You got to pass the producers. You got to justify the cost, and then you got to pass the consumers. And you got to develop that value perception. And any one of these points can choke off a technology. I'll pick on irradiation. Okay, that's Christine's favorite technology. You know, that's the technology of the future and always will be. You know, okay. It's never going to overcome this perception problem. No matter how you look at it, consumers, it's going to take something almost unbelievable to change the consumer view of irradiated products. You know, and the more and more this country is concerned with, you know, radioactive bombs and dirty bombs, and it's just, these are irrational human behaviors. And to overcome those things would take tremendous effort. I don't know if it could ever be done. But if you can, whether by luck or what, then you have market opportunities. So, you know, if I'm to summarize the whole experience that I have gone through in 16 years with high pressure, it is that a technology is successful because it offers some overwhelming benefits, either in terms of quality, convenience, safety, and cost. And then secondly, it has to be consistent with societal values. You can't sell things that people don't want emotionally. And high pressure does not tread on those issues, and therefore, like I said earlier, rightly or wrongly, you know, it's a gift. Second is that a new technology has to be fortunate enough to find early adopters that will reshape the industry. High pressure had the benefit of the academic science that took place in the 80s, and a lot of that really was at the sponsorship of U.S. Army NATIC. Those folks really had the vision, and if it wasn't for the U.S. Army, high pressure would not be a commercialized technology in the United States, and for that matter, probably even the world. And secondly, entrepreneurs are frequently the early adopters. Avomex is a great example. Avomex, if you don't know of the history of that company, this is the company that makes the guacamole product. Avomex started as a chain of Mexican restaurants. The owner wanted to bring in cheap avocados from Mexico, and he could not bring in whole avocados because of a trade restriction. So the only thing he could bring in was avocado pulp. Once you pulp avocado, you have no shelf life. So he didn't know that you couldn't do it. So he went and adopted high pressure, and now, you know, he is a very successful business. That company makes more money selling avocado than we make selling high pressure equipment to companies like his. Okay, that shows you when your customers are more successful than you, that's a good sign. So these entrepreneurs and these early adopters are very critical. And some of this is luck. It really is luck. And if the Army didn't come in when they did with the seeding of the research at the universities, University of Delaware, Wyoming, and this continuing today at Ohio State, Washington State, these places generate the legitimizing science that allows us to push this technology through USDA and FDA. I said in the early days, the worst thing is to say that this little company in Kent, Washington invented high-pressure processing, because we didn't. We're just benefiting from the work that others have done. And lastly, we find that a technology is successful because it's somehow aligned with some government initiative. And in the ready-to-eat meat area, for example, is the Listeria Directive that has given a lot of incentive for producers to go into high-pressure processing. It's given that extra kick necessary. Hormel was in the business already for their prosciutto product because they recognized that product as a relatively high-risk product. And they would have done that with or without government incentives because they said they wanted to be able to sleep at nights. It was literally their words. But since the USDA new Listeria directives, they were incentivized a little bit more to take this technology to the next step for their other products. So, reasons for industrial adoption: quality, food safety, higher yield, lower costs. For example, oyster shucking. No one wants to shuck oysters. Brand protection and government regulations. Industry adopt this technology because there is now market pull. People want this product. Costco wants this product. Walmart wants this product. And when those companies tell a producer, we are interested in buying your high-pressure treated sliced meat, there is now some response. New market access. When you can't sell your product overseas because of Listeria, you tend to want to do things that allow you to get to those markets. And innovation. Reasons that companies don't adopt technology would be these. It's hard to justify food safety. In the early days, we thought food safety was going to be the primary driver for high pressure. It is not. Food safety, maybe this is a little bit cynical, but food safety is something that people love to give lip service to. But when it really comes down to spending money, it is a very poor justification for most businesses. They rather buy some more chemicals or do something else rather than really invest in a new technology to achieve food safety. Now, that's not true for all companies. There are some companies that truly are visionaries and they really want to do things right, and those are the ones that are, in some ways, creating the market. Sunk cost of existing technology, that's a barrier. New technology is expensive, regardless of many of these technologies, what it is, it does involve high capital expense, and it takes guts to make those kinds of financial commitments. Price pressures in the marketplace. And lastly, sometimes companies don't have the imagination or the will to optimize for a new process. They want to take an existing product in the existing package and run it through a new process and expect it to turn to gold. That's not going to happen. You need to really understand the science behind it and then optimize the formulation, optimize the packaging so that you can get the most out of it. In Europe, there are still some unclear regulatory issues. There is the novel food regulation in Europe, and that is getting better. There are more and more companies in Europe now taking on high pressure. So this may not be an issue in another year or so in Europe. Lastly, there is really almost a strategy of do nothing in a lot of companies that we've talked to. They don't quite say that, but it's essentially that. And this last strategy, I've actually heard this from a company, in fact, a very, very big company, that said it is our what was it, strategy, or it is our policy not to be the first on any new technology, but we would buy the company afterwards, if it is successful. So consumers like certain things, and you have to meet those needs. Taste, nutrition, convenience, value, societal benefits. These are all things that high pressure can deliver fairly well. So, all said and done, the new technology adopter profile is this. It is an unencumbered decision-making process. Again, I'll go back to the early Avomex founder, Don Bowden. One man, one checkbook, decision made, okay? In a big multinational company, you have layers and layers of VPs and executive VPs and senior VPs and senior QA and senior marketing. Each one tends to want to hedge the risk by padding it a little bit. Well, I better add another $1 million to my marketing budget. Well, I better add another $2 million for plant innovations after the fact. And by the time you're all said and done, you're at a projected cost that nobody would sign up to. So having this ability is really critical. Now, big companies can do this. Hormel did it in a very early day. They had the leadership. They had a culture of innovation. They basically summoned us in the early days before we even had all the marketing going. They said, we've studied it, we know it works, this is what we want, give us a quote. Okay, so those people do exist. Companies that place a high value on quality, safety, new business opportunity are the adopters. Hormel, for example, I'll use them. They don't have a big presence in the ready-to-eat meat consumer sector. They're going to have, because they're going out to that area. They're going to pitch it to the consumers next. Right now they're in food service. So they're going to take market shares away from the other people, and that's going to drive the technology. Products that are significantly different from conventional, the lobster is a great example. No major sunk costs. So a number of the high-pressure companies are new companies because they don't have previous investments to deal with. This is an example of how Hormel markets their ready-to-eat meat product. I spoke to a salesperson for Hormel recently down in Florida, and she said that this is the easiest sell she has to do. All she's got to do is to go to the local school district and talk about lunch program. Okay, who wants to feed their kid anything other than the safest possible high-quality meat there is? So you have to communicate. This is stuff that Christine should kind of follow a bit. It's communicating the benefit to the food service sector. But ultimately, it comes down to, issues that consumers care about. Fewer preservatives, safer products. So the communication aspect is not a trivial one. You have to do this to educate your customers, whether it's consumers or our customers, you guys, as to the benefits of this kind of technology. So one last question is, people keep saying high pressure is a big company technology. Okay, so Avomex, I said, what about Avomex? These guys, as of about 2 years ago, were already producing over 1 million pounds a week of guacamole avocado products. And they're certainly not a Nestle or P&G or a Unilever or a Master Foods or a Conagra, But this is no longer insignificant production at this level. And they've done a great thing. High pressure processing is in use now for both microbiological and functional benefits. Food yield, quality, labor savings, and market creation are strong commercial drivers. And regulatory and consumer support are helping commercialization.
I'm sure Ed would take a few questions. Questions from the audience?
I got one, Ed, and you didn't touch on this on your cost analysis, but I think one point that's kind of interesting is you scale up to bigger size packages. It's probably a whole lot easier and more. You actually can gain efficiency. We're looking now at a 6-pound institutional size pouch. Get rid of those number 10 cans.
Yeah.
You guys like because we pay a lot of money to ship those around the world. You know, and again, you don't fill the whole box with the cans, and you do with the pouch. And then that fits a need in the food service. So part of your equation, I think, is the changing. When I'm reading that more than 50% of the meals are now purchased rather in the home rather than produced from scratch, there's a huge niche there.
Yeah, the larger the package, actually the more beneficial is high pressure because, again, there's no heat diffusion here. Whether we're processing a 1-pound package of ham or a 20-pound package of ham.
We don't have a 90-minute retort cycle for our trays anymore.
So package optimization is a big issue to commercialization, and if possible, these packages should even be made in a way that allows better nesting. One company actually makes packages that are pie-shaped because it can fit them together in a circular pressure vessel.
So if you're using water in this process, what about the rates for process contamination for package leaks? Does the pressure during the come up time and while it's reducing also, does it have any effect on the steel?
Yeah, this high pressure technology will find any leakers in your packaging, definitely. And the contamination that results, there are cleaning cycles that these machines can be sent into where the water is purged and appropriate detergents and sanitizers are pumped through the system to clean it. If there are bad seams in your package, it will come out waterlogged. So, that's what you get with this technology.
Cycle.
But Ed, I think the thing is, though, is that just like the package, the water in the vessel is also treated and receives the exact same microbial destruction. So there really isn't an in-process contamination issue.
You're just deleting your sample, perhaps, for your product.
Yeah.
Isn't related to that? There's a bit of a trade-off of your horizontal versus vertical machines until to recycling the pressurized fluid, and people have to get smarter at doing that. Right? When you reload the horizontal unit, you pretty much like the video from Hormel. The water's flowing in, and at the end, when you take it out, you got to dump that water.
There are kind of different ways of running the equipment. Some of the vertical machines allow you to maintain water in the cylinder, so you spend less time having to refill it. A horizontal system, you have to purge the whole thing, so the horizontal system can take a little bit longer to refill with water before you start your high pressure cycle. These issues are really driven by kind of plant-specific requirements. Sometimes a customer says don't have the vertical space for whatever reason. They don't want to invest in it. So a horizontal system would make better sense for them. A horizontal system doesn't require vertical space, but it takes a lot more horizontal space. So, one way or the other, you have to accommodate the equipment. The vertical ones have some advantage in terms of cycle time because of primarily the fact that you can keep a portion of the water inside the vessel between cycles. So after, maybe at the end of every shift, you can purge the whole system, and if there are any contamination due to leakage, you can take care of that. So it really depends on what product and how you're doing it and the details of your plant operation.